getting position. And it falls to it. So I was like, I thought it was great. That's what's like, so that's what's wearing the. Yeah, that's both. You have to get to really choose.
Just turning the lights off.
Because.
Okay, good afternoon, everybody. Keep on tracking through angular momentum. We're going to see, hopefully make it to it, but maybe one day. Something that will eventually tie all of this communication and discussion that we have here. It's going to tie back to our first lecture. See deflection of silver atoms and up and down states and things like that. They're all going to appear again very simply. Right? But it's not really clear how we go from here to that determination and that theory and that application, but we will. Somehow secretly we are doing the math of deflections of silver atoms or whatever we call spin. We're going to see that everything that we're discussing here can be applied to that. And it's not exactly clear how those are correlated, but we're going to see that they are extremely correlated. So I just give that as a little tip in the back. The really interesting thing about this angular momentum discussion is we're going to see that today in particular. I'm going to say next week. We're going to say next week. That this theory of the electron going around the proton, what we're going to learn from it, we can apply to a lot of different things. Kind of like the harmonic oscillator. It's just one of those really useful theories that's going to pay dividends for us. Angular momentum is one of the best tools we have to study all sorts of things in chemistry. We're not quite there yet. Still got to kind of get a handle on the quantum mechanics. We haven't even gotten there. We're just kind of approaching our quantum mechanical evaluation of angular momentum. We'll be able to start thinking about quantum mechanics today. I'm just going to recap where we were and then kind of recover the last 5 to 10 minutes of class and then trudge on from last class. So we're talking about angular momentum. We're talking about the rotation or the orbiting of an electron around a proton. And remember that we were solving the hydrogen atom. In last class, I just talked about that we're going to solve this problem with solve two different problems separately, then put together at the end. There's going to be the angular part of the electron whipping around the proton, and then there's the radial part, which is associated with the electrostatic attraction. You have the centrifugal force, the centrifugal potential, the rotation, the angular momentum, and then the electrostatic attraction. So we're stuck on the angular momentum part right now. Come back to the radial part later. And so we're just focused on, basically, we're fixing R here, fixing the distance between the proton and the electron. We're just thinking about the motion of the electron at fixed distance. So we can use angular momentum for that. The idea is kind of like you have a glue, like a rigid bar holding the electron and the proton together at fixed distance. Rigid bar, we call it like a rigid rotor, as we call it. So I think it's like a diatomic of a proton electron that doesn't vibrate. It's fixed like that. So when you give it some momentum, it's just the electron's just going to whip around. And it whips around with total angular momentum. The magnitude of the angular momentum is equal to the frequency of that rotation, right? How fast it's moving around this circle, omega, times its mass, its rotational mass, the moment of inertia, which is just a function of the mass of the thing on the end of that bar, the electron, the thing that's whipping, times the distance between the two particles squared. Okay, and this is just the rotational mass. When you're rotating, you can't just think about the mass, you got to think about the distance at which the mass is at compared to the center of mass. So we can't just say that the mass of the rotation is just m, like we can with linear momentum. It's got to be something that's dependent on, that gives you some shape of that rotation as well, because you have for constant angular momentum, you have two different frequencies for two different lengths, right? So we got to account for the fact that the rotor has some length to it, and that plays into the moment of inertia. And so you can think about the total angular momentum is a mass times the speed. And that's exactly like linear momentum. Linear momentum is a mass times the speed or velocity. And so the math works exactly the same. We've just, as I said before, we're just making the mass and velocity now rotational quantities that look a little funky. The physics works exactly the same way. We're just in a circle. So we can use this because we know momentum and linear angular momentum kind of have the same structure algebraically. We can use our understanding of momentum to come up with rules for angular momentum. And remember, ultimately, our goal is to calculate an energy operator, right? The Hamiltonian that accounts for the kinetic energy of angular momentum or the kinetic energy of rotation. And in linear terms, the kinetic energy is 1/2 mv squared, right? That's in linear terms. We have linear motion. So all we need to do is just replace these with our angular terms. So going from a line to a circle, we have t is equal to 1/2 I omega squared. Right, same idea. Mass times speed squared times 1/2. No different. Right? And likewise, we can also, because let me write it actually down here a little bit. Let me organize this a little better. Because we can use the fact that P is equal to mv, we can write that the kinetic energy is equal to P squared over 2m. And so when we go to our circle representation, we do the same thing again. We just replace our linear terms with angular momentum terms, and that's going to be L squared over 2I. All right, so the angular kinetic energy of the system is just the angular momentum squared divided by 2 times the rotational mass. I'm just making swaps. All the dimensionality of angular motion is the same as the dimensionality of linear motion, still moving in a circle, a distance that has units m length. We're just doing it in a circle instead of doing it on a line, rolling that infinite line together into a circle. And so all the math works the same. Okay, so the kinetic energy of the system Hamiltonian is equal to the kinetic energy. The total energy of the system for rotation is equal to the kinetic energy. And the kinetic energy is equal to L squared. So what we have to do in order to figure out what the wave functions and the energies are, we have to evaluate L squared as an operator. Right, so we have to come up with some quantum mechanical representation of L squared. All right, that's not the easiest thing to do, but we know what P squared over, we know what linear motion looks like. And my claim is that linear motion and angular motion are exactly the same. They're just on different coordinates, they're on different boundaries. Linear motion is just motion in a straight line, go on for infinity. And this angular is on some motional surface, some surface of all the possible points the electron can be at. That is a sphere. So it's still an infinite surface, still infinite number of points on a sphere. But it's in some sense, it's just a three-dimensional box that can be formed in the sphere. So if I understand what this looks like in 3 dimensions in X, Y, Z, if I convert this into a spherical representation of the space, if I know this and I can convert P squared into the spherical representation, then I get L squared out of it. L squared is P squared, but on a circle. Okay, so I need to convert from linear coordinates for P squared to angular coordinates, circular coordinates, spherical coordinates for L squared. Motion in a box versus motion on a surface of a sphere. Right, so my goal is to think a little bit about P squared and convert it over to spheres. Right, that's going to be our goal today. We've already gotten that started a little bit. All right, so we're saying that the operator T is equal to the L operator squared divided by 2I. Right? And we're saying that this is basically equivalent to P squared over 2 times the mass, whatever that is. Right? And that's going to be equal to, just by definition from before, looks just like our 3D particle in the box, minus h bar squared over 2me times the second derivative amongst all 3 directions. Right? We're moving in the box. The sphere is 3-dimensional, so we need to consider all 3 dimensions. So this looks like the kinetic energy of a particle in a 3-dimensional box. Okay, but we have to make sure that what our boundary, our surface, kind of where the things are limited to be on this, is that at fixed R. So this thing's allowed to move. The potential, or kind of the space in which we define the problem, is at fixed distance. So we'll be able to make some simplifications when we convert from x, y, z into spherical coordinates, the coordinates of a sphere, because we won't have any changes in R. We're going to have some changes in R. Something looks like d by dr, once we do the conversions. And all those terms are going to be 0, because we're fixing R. So this is completely general, but we have a symmetry and we have some constraints to our system, which is that they're at a fixed boundary. They're on the surface of a sphere. So I'm just going to bring our coordinate system over from last class. Okay. So this is our coordinate system, right? We have an electron at x, y, z. And we're going to define that position with 1 vector length, r, and 2 angles. So I'll write these really quickly. So r is just the length of the vector, which is the square root of x squared plus y squared plus z squared. Of course, that can be any value greater than or equal to 0. Defines the size of the sphere that my electron can exist on. There's the angle theta, which I've drawn in blue, sorry. And I'll give you a description of these in just a second. It's the inverse cosine of z over r. All right, so this is the angle subtended between r and the z-axis. Okay. So the z-axis goes from positive to negative, and it can either be, it's 180 degrees of phase, if you will. It can either be up or you can be all the way down. It doesn't really matter if you're on the other side of the circle because they're all the same value. So this just ranges from 0 and pi. Right? Pi would be a system pointing, a vector pointing completely downwards. Okay, and then finally we have phi. It depends on who you ask. Mathematicians, in fact, I don't know if this is true, you guys remember from multivariable. I think mathematicians put phi here. It's the angle between y and r. But physicists put it on x. Kind of a weird notation. But I find it useful to use x because I think y is kind of like the pariah of the coordinate system. X and z are the superior ones, so we're going to use them. But that's just me. And that's the inverse tangent of y over x. And of course, this basically tells you in the xy plane which y pointing, so it can subtend 200, 360 degrees. It goes through all 4 quadrants of the xy plane. So phi can be any value between 0 and 2 pi. Okay. So these 3 coordinates give me a representation of every point in space, but now at fixed r gives me all the points on the surface of a sphere at radius r. That's going to be very useful for us. That's going to be a really useful way to think of things, because we don't really care about linear motion of our electron. It's bound to the proton. It's only moving in circular orbits or elliptical orbits. And so we don't really, if we fix r, we only need those 2 coordinates, which are the polar coordinates, if you will. In some sense, polar coordinates that tell you where the electron is in terms of the 2 different angular dimensions that you have in this system. And so that's a really, really convenient use of numbers for us. Here's the problem, right? I'm going to have to now take these second derivatives up here, d by dx squared, d by dy squared, d by dz squared, and convert them through the chain rule to d by dr squared and d by d theta and d by d phi. Right? And so I'm going to have to take derivatives of these conversions, right, and start putting terms together to do my conversion between x, y, and z and r, theta, and phi. Right? I need to do a coordinate change. And so even though what we're going to find is, yeah, the coordinate system that I've chosen is really nice. It makes a lot of sense. But I know that when I write my kinetic energy, it's going to have some cosines maybe. It's going to be kind of ugly. I got to take derivatives of cosines and tangents and square roots, and it's going to be really ugly. So we're going to have to manipulate the math a little bit and try to understand what this is going to look like, what the kinetic energy looks like in terms of our angular coordinates. Right, so I'm not going to go through that math. It really is brutal and it's not fun. I had to do it as an undergrad, and I didn't find it to be particularly helpful. But I think it's helpful to write it down and look at what the kinetic energy looks like in terms of angles and radius, because we can get some physical interpretation, right? Some nice physical things that we can look at. Okay. Oops, that's the wrong document. Okay, so I want to take this strange sum of second derivatives, right? And I want to convert into r, theta, and phi, right? Using the formulas I have for this conversion on the other page, right? I'm going to have to solve for x and y and z and then do substitutions, a bunch of chain rules, get conversions. I don't know if you learned it in Calculus 3. You learned about the Jacobian. You can calculate the Jacobian for this transformation. I don't know if they teach that in Calc 3. But so it's a bunch of like tedious algebra. And so I'm going to break it down just like there's 3 separate terms. There's an x term, a y term, and a z term. There's going to be an r term, a theta term, and a phi term. So we'll break them down into 3 terms. So that we'll do the r term first. And as you can see very quickly, the term for radial looks very complicated. It's got a bunch of r squareds in it. And if you take a derivative of a derivative times a function, it's really, really ugly. But if you look at it, if you blur your eyes enough and do some really, really lazy calculus or lazy algebra, you'll see that this really looks like r squared times 1 over r squared times d, the derivative of the derivative, which just looks like d squared dr squared. Right? That's what that kind of algebra works out to. If you think of all of these as algebraic variables, if you can commute them. You can't commute these because you're taking a derivative of a product here. Right, but you can kind of see that it does look like the second derivative of r, at least in terms of dimensionality. Right? This is the radial term. But for angular momentum, we don't have to think about this term at all. Because remember, the radius is fixed. So whatever motion the system is doing in terms of angular momentum, r is not changing. So d by dr the gradient along R, how much the energy is changing as you change R is 0, because d by dr is 0. So this whole term, at least in our case, goes away. So for 0 for angular momentum, we don't have to think about it. Our physics do not depend on R. Well, they do depend a little bit on R because the moment of inertia depends on R. But we don't have any dependence on the change in R. And we're going to see some dependence here, because when we look at the other terms, we get what's called the azimuthal term. That's the z-axis. Angular term. Right. And let's look at the formula here. This looks a little different, but here we get a net d squared d theta squared, just like we should expect. Then we get 1 over sine squared r squared sine theta. What this is telling you in some sense is, right, if theta is 0, right, if theta is 0, that means that the electron is directly along the y-axis. Okay, so there's no angular, or is it z-axis? There's no angular momentum along the z-axis because it's not precessing around it. And this term blows up, which means that the system in some sense wants to precess. Okay, so if this goes to infinity, we'll write this here. This goes to plus infinity as theta goes to 0, right? And what that's telling me is that the electron does not want to be right here directly on the z-axis, or what we call a gimbal lock, where it can no longer rotate along around the z-axis because it's on the z-axis. There's no rotation anymore. There's no angular momentum. And so this is impossible. And so what it means is, so here, this is only possible if the t is equal to infinity. And what this means is that as the system gets faster and faster and faster, the electron is at some angle relative to z, and it has some angle, some precession angle, where it's precessing around its axis. Okay, so the idea is, what this term is telling me is that that the only way to get my top to stand perfectly up top like this, is to have infinite kinetic energy. Okay, so what this means is that the electron at any finite energy is always going to have some precession. It's always going to, like the Earth revolves around its axis at 6 degrees, right? It has a little tilt. And this is that little tilt. So we call this, I don't remember what the astronomers or the geologists call this. I think it's called axial tilt, like the Earth. Right? In order for the Earth to be perfectly on its axis and rotate, it has to have infinite. That's what that term tells me. Kind of cool. And then finally, we have the last term, which is 1 over, oh, sorry. This is r squared sine theta, excuse me. There we go. So that gives me the right dimensionality now. I cancel out now. They should. The other one is r squared sine squared theta times the second derivative in terms of phi. Oh, sorry, that's not my phi. My apologies. I used a different label than that. Right, and this is our xy angular momentum term. XY plane angular momentum. Okay. And so all this is saying, again, is the same idea. The kinetic, the system, what this is telling me is that it wants me, this is pushing my as my system slows down, it's pushing my angular momentum vector, my rotational axis, towards the XY plane, right? But think about a top. When you spin a top, man, I think I actually have a top with me. When you spin a top fast, you can think about the top of its axis when it has a lot of kinetic energy is pointing. Yes, I do have one. A really crappy one, right? Because this is the top. This is my z-axis. When it has high angular momentum, right, you can see it processing like, I'm sorry, you guys can't all see this. So z-axis is pointing straight up. Okay, and you're gonna, the angular momentum vector of the system, if you will, or the R vector, is the little nipple at the top here. Right? So I pull it fast, right? And so the angle relative to z and the R vector is very small, right? It's kind of like this. Right? And what happens as it starts to slow down, the second derivative of the gamma starts to kick in. It starts to get wide, right? The oscillations begin to get wider. The z angle theta starts to increase. I really spun this really good. Right? And there's more displacement along the XY plane, right? It's trying to trace out a larger and larger circle each time. Here we go. Now it's starting to wobble. Right? And so that's the influence of that third term. Drawing, it's basically, as it slows down, it's drawing the R vector into the XY plane and causing the rotor to now expend larger circles of its rotation. I really asked this. Right? So those terms, complicated mathematically, but physically, they make a lot of sense. They just describe exactly the behavior of a top, meaning that you have to put in a lot of energy to get it standing straight up. And as it slows down, the XY plane starts to influence it and it starts to sweep out wider rotations around the z-axis. Now it's, as you can see, like pointing like this. Okay. All right, so those are our three terms. All right, we'll return to the radial term when we talk about the radial part. This term will come in back for us when we think about the springy part, the jelly part of the electron, right? The stretching action that it has against the electrostatic force. That term is going to come back. Okay, so we'll just hold on to it for now. Okay. So altogether, we can say that the Hamiltonian for rotation is equal to minus h bar squared over 2I times 1 over sine theta d by d theta of sine theta d by d theta plus 1 over sine squared theta d by d phi squared. So again, this is the energy driving us towards the z-axis, and this is the energy driving us away from the z-axis. Competition of two forces, two kinetic energies. One that keeps you in place, and the other one that drags you into the XY plane. So you always have a balance. All right, so our goal now is to take this, right, and find wave functions, psi. Then when I put psi in here, I get the energy of rotation times psi. That's the Schrodinger equation, right? That's always our goal, is to find a Hamiltonian for energy and solve for the wave functions that satisfy its measurement properties. Right? That when we take the measurement of the energy, that we get the energy back times the wave function unchanged. Now we have a two-dimensional function to deal with, right? And look, the phi and theta. So theta doesn't have, in some sense, the theta motion has no dependence on phi, but the phi motion has dependence on theta, right? And we saw that as theta starts to increase, the XY momentum starts to increase. So these are coupled. These are not independent variables. They're dependent variables. Phi, the motion on phi depends on the angle theta. So that's a complicated problem. Okay, but the idea is that this wave function here, right? These correspond to stable orbits at radius r. Okay, so that's all what we wanted to look for in the first place. So we fixed, right? That's what Bohr wanted to do in the first place. We fixed r and we find all the stable orbits. That's actually a little different than the way he did it, because he thought about the r's that lead to stable orbits. What I'm looking at now is I'm fixing r and looking for stable orbits at a fixed r. And what we're going to see is that what Bohr screwed up is Bohr assumed that in some sense that there are only values of r that lead to stable orbits. But what we can show is that there are, within a given value of r, there are multiple solutions, there are multiple stable. So he actually missed, in some sense, a vast majority of the possible solutions. He assumed that r is the thing that matters. But as we're going to see, r and theta and phi matter independently of each other. And for a given r, there are different theta, there are different stable orbits there. You've seen these stable orbits before, you just haven't realized it. And we'll see that today. Okay. I don't want to write down the equation for the wave function. Right? Don't really need to worry about what the equation looks like just yet. We will. Instead, I want you to get a physical sense of what these solutions look like. What do these stable orbits look like? Okay, and then we'll go back and look at the math. Okay, so our solutions are wave function psi which are functions of theta and phi. That represent stable orbits of some fixed amount of angular momentum. Okay, and what I'm going to do is show you pictures of the solutions. They're two-dimensional objects. So these are an object, a function has two dimensions, is a surface. The third dimension is you can think about theta and phi being the x and the y axis. And the theta or phi, or sorry, psi, the wave function, is the z axis. So these are three-dimensional objects. So I can make pictures of them. It turns out that the solutions for this complicated equation that we wrote down have been well studied for a long time. And in fact, the solutions are similar to the different stable electric fields that can exist. Someone's calling me. Can exist on the surface of a sphere. So imagine you have a conducting sphere, right? Like a I don't know if you ever remember those balls, like you go to the called Van de Graaff generators, or not Tesla coil, Van de Graaff generators. Those balls that are charged at the science museum, you put your hands on and the sparks come out of it and your hair lights up and stuff like that, really low current. You can think about these are the solutions of the electric field on a Van de Graaff generator. Similar functions that define the electric field. And they're called, they have a very special name, and we can look them up on Wikipedia. They're called spherical harmonics. It's not a coincidence that this looks a lot like harmonic oscillator. Again, these are harmonic oscillators on a sphere. Now, harmonic oscillators are one-dimensional linear objects that vibrate like this. But what if you have something that oscillates and vibrates on a spherical surface? Well, that's a spherical harmonic. Kind of interesting. Same connections between everything, right? So this is the solution of some stable oscillations of a wave on a surface of a sphere. We can also say these are standing waves propagating on a sphere. Very, very similar to a harmonic oscillator. And of course, the difference about a harmonic oscillator is that it's vibrating and its distance is changing. So the spherical harmonics are exactly the same thing because R is fixed. But the solutions will look like oscillations. They'll look like waves propagating on a spherical surface. That sounds very quantum mechanical to me. So let's look at the solutions to these. Oh, okay. Well, screw me, I guess. I was trying to copy a picture over. Let me grab it really quickly. Yep, this is it. Let's do this one. Okay. All right, sorry about that. Copy this over. Actually, let's just put it on a fresh page. Let's look at them nice and big. Oh, it was so big that it crashed my computer. Hold on a second. That was a little too exciting for program. Okay, let's try this again. Should have an auto save. No auto save. I doubt it's in here. Yeah, I doubt it's in there. All right, well, whatever. We can just continue. Okay, here we go. Okay, so here's a table of the first selection of spherical harmonics. You can't really read that. I'm sorry. I'll cover it. I'll write the labels down in a second. All right, so there's our spherical harmonics. Okay, they're labeled. Because we have two variables, we have two quantum numbers. Just like we had with the harmonic oscillator, we had one-dimensional motion. We had one quantum number associated with it. We now have two angles, and so there are two quantum numbers. And so the first quantum number we call L, right, which is what's called the angular momentum, total angular momentum. Right, we'll look at the math of this more carefully in a little bit. And then there's another number called M, which is called the azimuthal quantum number. All right, this has something to do with the z-axis, as we'll see. Okay, and so L can vary between 0, 1, 2, 3, just like always. They're quantized. We have 0, 1, 2, 3, 4, 5, 6. So each of these rows are the stable orbits of our system. And so you can see the coordinate system is slightly different for them. So let's look at this. So what we have actually is a solution to this problem that is zero angular momentum. And there's exactly one stable orbit. Right, so this is angular momentum free. Right? And the stable orbit is a sphere. Right? What does that mean? That means that the electron basically in this state can be in. It's completely perfectly delocalized. The wave function of its angular distribution, these are the wave functions that tell you something about probability, is just a sphere. The electron is completely delocalized over the entire sphere at big star. Okay, there's only one of them. Right, and we say that the value of that m, that second quantum number, is 0 for that. Now let's go to L equals 1. Now we've given our system 1 unit of angular momentum. And now what we see is we have 3 different solutions. So we have one for 0, one for plus 1m, and one for minus 1m. And we can see that these aren't exactly spherical anymore. They kind of have a peanut shape to them. Right? What does that say? Well, the important thing to notice is that, first of all, the sign changes. So these are odd functions, whereas this, of course, is an even function. Right? And we can see that each of these are aligned along one of the axes. Right? This one is lying along the x, this is lying along the z, and this is lying along the y. Right, so we often call this the x, this is the z, and this is the y orbital of the L equals 1. And what does this tell me? Well, it tells me that an electron that has 1 unit of angular momentum in the hydrogen atom is that it has a choice and tends to oscillate like a top. Right, where its axis is pointing along one of the 3 possible axes that you can have, right, x, y, or z, right? So you can imagine that what this is pointing out, what this is mapping, is the average or the possible positions that this top is pointing as it's rotating. Okay, so at L equals 0, what this is saying is that the electron looks like it has no particular orientation at all. Electron can be anywhere. And it can be oriented, it can be, well, it's not rotating, it's not angular, there's no angular momentum, it's not rotating at all. It's just completely delocalized. And so L equals 1, these are the first states that have some spin to them, some angular momentum. And what it says is that the electron can be, its little nipple here that's given its direction, its radial position, or its angular momentum vector, is either pointing along the x, the z, or the y axis. Okay, so you can have, so that means you have a top that's polarized toward one of the 3 axes. That's how we write about that. And then as you go down, increase L, you can see there are more and more choices and they get more and more complicated. You can see now we have, for L equals 2, we have 2, we have 5. For L equals 3, we have 7, and so on and so forth. Okay, we give these names in chemistry. You probably already get a sense of what these look like. Right? These are the SPD F orbitals. Right? So we call the L equals 0 the S orbital, the L equals 1 the P orbital, L equals 2 the D orbitals, the F orbitals, the G orbitals, the H orbitals, and the I orbitals. And then so on and so on. Okay, so the orbitals of the hydrogen atom, the electron orbitals, are just the angular momentum states of the electron. They tell you how the electron is moving around the proton. The p orbitals are 1 unit of angular momentum. The s is 0. Remember what I said about Bohr's model. Bohr's model, when he thought about stable orbits having to be a function of r, where he thought about r and angular momentum together, right? He wanted to balance the 2 forces of centripetal force, the centripetal force, and the traction force from the electrostatic. And when he did that, he got some stable solutions, but they required that they always were spinning, that there's always some angular momentum in the system. But when you treat the radial part separately from the angular momentum part, and then you do all the right quantum mechanics, you find that you can, in fact, have a state for the electron that has no angular momentum. There is a stable angular momentum free rotational state for the electron and a proton. It doesn't get sucked in, contrary to what Bohr thought. Actually, that just resolves our problem in general, right? What this is saying is that no matter what I do, no matter what energy I'm at, the electron is never going to get sucked into the proton because the lowest energy state is just localized over the sphere. It's never in the center, it turns out. So the electron never gets consumed by the proton. Right? So somehow we've already resolved the contradictions from classical physics by just getting rid of classical physics and doing things the right way. That's why I said that Bohr got the right answers for the wrong reasons. Because he did it the wrong way. He didn't understand quantum mechanics. But when you apply quantum mechanics to his insight, you get the right answer. Right? So of course you may ask the question, why is it that there is how can you have the electron be in a state that has no orbital angular momentum? It's not moving from our point of view, but somehow is not getting sucked in. Right? There's no centrifugal force in this state. There's only attractive state. So it's only attraction towards the center of the atom. So what gives? How can that be possible? Well, remember what these are. These are states of constant energy, constant rotational energy, right? How did we solve these? We can, I deleted it because it crashed, but we constructed a Hamiltonian that defined the angular kinetic energy of the system and solved for the wave functions. What do those wave functions represent? They represent states of fixed energy. So we have a well-defined energy for these systems, meaning that we have a well-defined magnitude of our momentum p squared. So what we're doing is by defining a state of constant energy, we're losing position information. We have a well-defined energy and therefore a poorly defined position. And so it turns out that the lowest energy state of a symmetric potential is a state of that we treat as a state of constant energy, is also a state that has no positional information. Right? By defining the energy to be exactly zero, right, having a zero energy state, that means we have no information, zero information about where the electron is. The only possible way to have that is a state in which the electron is delocalized like a sphere, has no positional information. So the reason why the electron does not get sucked into the proton, in some sense, is due to the fact that we don't know position well enough. By defining an atom in the stationary state of a 1s orbital, by definition, it is not defined with any positional information, and therefore the electron is delocalized completely. It just had no possibility of ever hitting the center, it turns out. Okay, so that's a consequence. The stability of atoms is a consequence of the uncertainty between, or rather the wave-like nature of the system, which reveals itself as an inconsistency or an indeterminacy between position and momentum. And that's why it can have this angular momentum free state, why it can orbit with no energy, because it's just delocalized by its nature as a wave. In some sense, the most stable field, the most stable wave on a circle is a wave that's propagating in the same way everywhere. It's kind of the idea. It's very cool. So it's not so surprising that they figured this out pretty soon after Bohr screwed up. I give Bohr a hard time. He's actually much smarter than I give him credit for. Okay, so let's look a little more carefully at these spherical harmonics. Let's see if we can learn a few things from them. Okay, I'm going to give you some notation first, because we'll use this notation. Let's talk about some properties of the spherical harmonics. So these wave functions, remember, these are rotational wave functions for our electron that are that are angles that are dependent on the two angles. We have a label for these. Right? We give them the label y. Or am I going to label y? Y, I have no idea. Zero idea. And we label them based on the two numbers. So there's the L and the M number. And they're also functions of theta and phi. Okay. And they have all the properties that we want. Right? They're normalized. Okay. So the integral of y squared is equal to 1. All right. We'll have to look at that a little bit later. I'm not really sure how to integrate over these functions just yet, because we haven't really dealt with angles. We'll have to think about that. They're orthogonal, right? Which says that the integral of y with different m's or different l's times y with a different m or a different l, d theta d phi, is equal to 1 if the l's are the same and the m's are the same, and 0 otherwise. Okay, so they're orthogonal, just like we want. Right? And as we'll see, they're oscillatory, right? They have all the properties that we want. Quantum channels. Normalized, orthogonal, so on and so forth. Okay. They provide, they have two indices, as I wrote before, which we call quantum numbers. Okay. There's L. This is what's called the total angular momentum. Okay. And L can be 0, 1, and any other number, any positive number of 0. And then there's M, which is called the azimuthal quantum number. You might not know what azimuth means. It's an old navigation term. Azimuth is this axis when you're a navigator and you're looking at the stars. So of course there's XY, which is important when you're a navigator, but there's also this when you're determining things from stellar coordinates. You got to think about this direction of azimuth. So that's the Z axis. And M, interestingly, can take any number between minus L and L. Okay, right. Remember, we saw that if L is 0, M can only be 0. There's one stable orbit for L equals 0. L equals 1, there's minus 1, 0, and plus 1. There's 3 stable orbits. 5 stable orbits for L equals 2. Okay, so we can say that there are, for a given L, there are 2L plus 1 stable orbits. All right, we're going to see that 2L plus 1 number come up a lot in this class. It's a really, really useful relationship. Now, what do these L's and these M's correspond to? Right? They're quantum numbers that represent a certain measurement that we do. Remember, quantum numbers are labels that represent the results of a certain measurement, right? We have the first energy, the second energy result, the third energy result, the first angular minimum, the second angular minimum, right? Each of these labels label a specific state. So what do these represent? What results, what experimental results do these correspond to? What do they index? So I think that's a nice way to think about it. Okay. So in order to think about what these correspond to in terms of angular minimum, it's best to, again, look at a picture of vectors and XYZ coordinates. Oops. I want the line. There we go. All right, so there's my coordinate system. Z, X, and Y. Okay, so we have an electron. What we're gonna do is we're gonna embed an electron here in our origin, and then so we have an angular momentum vector pointing in this direction. Okay, so L is pointing in some direction relative to the z-axis, the azimuth of the atom. Okay. We can always write this as a set of components, right? So there's an LZ component. There's an LX component. Right? And there's also an LY component. In this direction. Right? Let me do it in a different color. LY component. Right? So we can always write L as a vector, LX, LY, LZ. Okay, and the length of L, so how long L is, the total angular momentum, right? This is the magnitude of the angular momentum, right? Which is a scalar quantity, is going to be equal to the square root of L squared, which is equal to LX squared plus LY squared plus LZ squared. Right, so L squared gives us something like length or magnitude. Okay, some L squared. Seems like that's a useful thing to measure a length. Right, and we can do with a little bit of math what we can show is that L squared on our angular or spherical harmonics gives us a beautiful little formula, which is h bar squared L plus 1. Let me clean that up a little bit. Times our wave functions, our angular momentum wave functions. So L, this is why L is our total angular momentum quantum number, because our magnitude of our angular momentum, how long the vector is, the square of its length, is proportional to L plus 1. So I can say that the length, the total angular momentum of the system, therefore, the magnitude of the angular momentum is h bar times the square root of L plus 1. Okay, so L gives you a length of a magnitude of the angular momentum. So as L increases, the system's spinning faster and faster and faster and faster. Okay. And what we can show, and we'll talk about this more carefully next class, is that we can measure y LZ, right, which is the z direction of this system. And that's equal to h bar m times y LM. Okay. So M tells you something about the way in which L is pointing relative to the z-axis. Okay. Whether it's pointing as close to the z-axis or it's perpendicular. Right. So it tells you something about the orientation of the rotation. Right? So L squared tells you how fast it's rotating. Fast it's rotating. LZ tells you something about the angle in which it's rotating relative to the z-axis. So for instance, if L is pointed up like this, this is my thing that's rotating. There's an electron here and it's like a barbell here, two atoms on each end. And L is pointing in this direction. My molecule is rotating perpendicular to it, right? It would be like this on my elbow. Right? But if I have my angular momentum vector in this way, my molecule is rotating this end over end like this in front of me, like a propeller prop. But if I put it like this, right, it's now rotating at a slightly different angle relative to you. So this is an orientation number, right? This tells you about the angle, and this tells you the speed. But here's the problem, right? I don't really know exactly I don't know exactly what the orientation, these two numbers, what exactly the orientation of the electron is. Because I don't know the other two axes yet. Right? Because if my L is pointing in this direction with this LZ, right? This L can be in any direction, can be in a circle, and all of them are successful, right? L can be here, right? Let me do a different color. Right? Anywhere along the z-axis. Right? Any of those values are perfectly acceptable for L. Right? So just by knowing these two numbers, I can say that L is somewhere on that circle, but I don't know where. Localized around that circle. These are all the possible directions of L. So given L squared LZ, this is all possible directions for L. So the system's not well determined yet. Right? But we kind of get a general sense of what's going on. But we don't really know exactly where L is. What we're going to find out very, very soon is that this is the best we can do. We can't know X and Y. We can know Z. We can know L, the magnitude, and we can know one of the directions, but we can't know all three. Right? So this is literally the best I can do. And in some sense, I've already spoiled that, because if we could know X and Y, there would probably be numbers like M that correspond to the direction in terms of the X and the Y direction. But the spherical harmonics only depend on the magnitude and one of the three directions. There are no other M numbers here for the other directions. If we knew those, if we could measure LX and LY, there would be an M and an N and a Q or something, that one for each one. There's only one of them. So I know I can't measure the other two. It's not clear why, but next class we'll answer that question. Why can I only know one direction? Again, these are the consequences that we have due to the fact that these systems are delocalized. In some sense, we know that because of the fact that the electron, say, in the s orbital is perfectly delocalized, it can be anywhere on this sphere. We know that the tools that we have to measure are, by definition, limited. They have to be. Because if we had the tools to point where the electron exactly was, then it would never look like it could be a sphere. So we can always pinpoint it. But it is a sphere. That means that we don't have the tools. That's the best we can do in some sense, is to determine the 1s orbital as a sphere. Because that's the only two things that we can measure. So there's kind of like a chicken and the egg argument here, right? The consequences of these states are a consequence of our lack of information. You can also say that because the way the states are, that's why we have a lack of information, which way better think about it. But let's look at this a little more carefully. Okay, so let's just look at a couple of examples. All right, so let's just draw some vectors for different states and just see if we can get a sense of what these different states look like from the point of view of just motion. Okay, so we'll look at the L equals 0 state. This is what we call the S state. Okay, the only allowed value of this is m equals 0, right? So what does this mean? This means that the length of the angular momentum vector is h bar squared 0, 0 plus 1, which is 0. Okay, and LZ by definition is 0. Okay, so that's a really nice function to draw. Remember, it's at fixed r. So we have some r vector here. Right? And r can be in any direction. And the wave function can be anywhere, right? So r can be in that direction. R can be in this direction. It can be in some other direction, right? I can point a direction and draw a circle in which the electron can be in any r, and those are just, all those vectors are all pointing the same, all different directions are all the same length, so that's just a sphere. And I'm just basically drawing a sphere, but with a bunch of circles. Okay, this is just a sphere. Okay, that's really boring, but that explains why it's a sphere. The angular minimum is 0, but remember r is non-zero. The electron has to be at some distance, so it's got some r. The r is not moving, and the r can be anywhere. So that draws a sphere out. There's no preference. R has no preference. The r vector has no energetic preference for any position. Okay, because there's no L. There's no centrifugal force. So R can be anywhere. Sphere. Simple set. All right, so let's try L equals 1. All right, this is what's called a P state. You may be interested why they're called S, P, D, and F. It's kind of interesting. S is called specular. P is called, you know what? I don't remember what they are anymore. Principal. D is diffuse. F is fundamental. And after that, they just made them up. There's like, okay, well, after F is G, then after G is H. It's really dumb. All right. I don't know why they're called SPDF. There's some history on Wikipedia, but they have some old school names. So let's look. So the magnitude of our vector L is h bar squared 1 times 1 plus 1, which is root 2 h bar. Okay. And M can be either -1, +1, or 0. Right? It can be any value between minus L and plus. Different by one. Okay, so we have 3 possible vectors that we can choose. Right? So we have one. Right? We have the first one we have is LZ is equal to 1 and length root 2. So that's a vector that looks like this. Right? So there's our M equals 1 state. Right? So that corresponds to, let me think. So L is in this way, L is this way, so it's this way. So it's rotating counterclockwise around the z-axis. Oh, that's the wrong way, counterclockwise. There's the M equals 0 state. Right? That has no component on the z-axis. So that means that the angular minimum component, let me erase this, is directly on the xy plane. Okay. So it draws a little circle in the xy plane. And it's orbiting in this direction. Okay. And then we have the M equals -1 state. Right, which is pointing downwards now. Okay. And is precessing in the opposite angular velocity way than the M equals 1. So one of these is, so if the angular minimum is pointing in this direction, that is this rotating. The electron is kind of precessing about the z-axis. This one is precessing in the xy plane. And this one is precessing now on the bottom axis, moving in the opposite direction as the M equals 1 state. Okay, it's not really clear exactly. Right, you can kind of look at this one and say, okay, that's my PZ state, right? Like it kind of is pointing this, or this is my PZ state, right? Like it's pointing in this direction. It's really clear. It's not really clear how these are correlated to any particular direction because L is pointing not really along X, Y, or Z, exactly. How pointing some random direction like this, right? So it's not really clear how to go from these vectors into the PX, the PY, and the PZ orbitals we saw in the previous picture. And so we're going to have to look at that a little more carefully. So it's not so clear how we get PX, PY, PZ from these. Right, but it should be clear from the L equals 0 state. Right, this obviously looks like a 1s orbital. Right, it's just a sphere. We know that the 1s orbital is just a sphere. It's not so clear how we get from these motions of angular momentum vectors, how we get PX, PY, and PZ. So we'll have to look at that math a little more carefully. It requires us to actually write down the equations for the wave functions corresponding to these angular momentum states. And so we have to think about the spherical harmonics of these states. And we'll see that, in fact, these two states right here, M1 and M-1, they're complex functions. And so in order to get Px, Py, and Pz, which are real, and they're real functions, they're real wave functions, we have to get rid of the i's somewhere. Right? We're going to have to do some combinations, remove some imaginary numbers, and do a little bit of algebra. And we'll be able to go for these three motions and get to the p orbitals that we know and love from atomic chemistry. Okay, so that's where we're at. We'll do some more explorations of angular momentum very soon. Otherwise, I'll see you guys on Thursday.